Welcome to This Explainer. Today, we're pulling back the curtain on something truly fascinating. Whether you're looking at a retirement stock portfolio, corporate earnings reports, or even just your own tax bracket, you're actually looking at the surface of a powerful, completely hidden mathematical engine. It's literally the engine that keeps the modern global economy running. And today, we're going to see exactly how it works. Seriously, think about that for a second. How do you find perfect balance in an economy with millions of moving parts? I mean, you've got consumers, corporations, raw materials, interest rates, global supply chains, and they're all interacting at the exact same time. Human intuition simply isn't enough to untangle all of that. Math is the only tool we have that's capable of solving such massive, multivariable chaos, and it brings order to what otherwise just looks like absolute randomness. Okay, let's dive into this. Here's our roadmap for today. First up, math, the economic backbone. Then, solving with linear algebra. Next, the Gaussian elimination method, followed by Gauss versus Gauss-Jordan, and finally, optimizing the economy. Section 1. Math, the economic backbone. So modern economics is way more than just abstract philosophies. It requires some intense, rigorous math. And you can see this structured framework in action all around us. Investors use it to balance stock market portfolios. Corporations rely on intricate equations to model profit while factoring in things like inflation and interest rates. Machine learning algorithms chew through immense data sets to predict consumer behavior. Even the highly secure encryption behind blockchain or the algorithms figuring out your optimal tax deductions, they are entirely driven by complex math. At its core, economics is all about demonstrating cause and effect relationships. Now, if you're only looking at two variables, say the price of a cup of coffee and the quantity demanded, simple graphs work just fine. But real-world problems, they are never that simple. When you need to track the cause and effect of countless intersecting factors on a massive global scale, you kind of have to leave simple geometry behind and break out the heavy mathematical machinery. Section 2. Solving with linear algebra. Now, what's really interesting about this is how linear algebra helps us organize all that overwhelming economic data. When we have thousands of variables, economists use what's called an augmented matrix. Think of this as a spreadsheet on absolute steroids. Instead of staring at a chaotic mess of algebraic equations with x's, y's, and z's, you just strip away the letters. You organize the core numbers, the coefficients and the constants, into a clean rectangular grid. It's a way to track market chaos in a highly organized mathematical space. But getting the data into an augmented matrix is really just the first step. You still have to solve it, right? The goal is to push that matrix into what we call row echelon form. It basically looks like a staircase pattern. The all zero rows sit down at the bottom, and the leading numbers systematically shift to the right. By physically pushing the data into this staircase structure, a completely tangled web of equations is simplified into a readable, solvable state. Section 3. The Gaussian elimination method. So, how do we actually create that beautiful staircase pattern? Well, we use Carl Friedrich Gauss's brilliant method, specifically the forward elimination phase. It's a flawless step-by-step algorithm. First, you search a column for a non-zero pivot entry. Second, you swap rows to get that pivot right up to the top. Third, you subtract multiples of that pivot row from the rows beneath it. And finally, you just repeat that process until the staircase takes shape. It's a purely mechanical process that economists use to distill raw data down to core answers. Once that elimination is complete, the math connects straight back to reality. The shape of that reduced matrix tells us exactly what's happening. If you get a unique solution, perfect. It means equilibrium in the market has been found. If you get infinitely many solutions, your market is highly flexible, and variables depend on shifting parameters. But if you end up with an inconsistent system where equations literally contradict each other, like math saying 0 equals 14, it tells you that the market you're modeling is completely broken. No solution exists. Section 4. Gauss versus Gauss-Jordan. Now, when economists are crunching these massive systems, they face a critical choice. The standard Gauss elimination method stops at that upper triangular staircase we talked about, which means you have to do manual back substitution to find your final variables. But the Gauss-Jordan method takes it a step further. It reduces everything directly to a diagonal line of ones, yielding the variables instantly. Sounds amazing, right? A much more direct answer. But there's a hidden cost. And this brilliantly illustrates that cost. It all comes down to computational power. If we compare the two, Gauss elimination operates on a scale of n cubed divided by 3, while Gauss-Jordan is n cubed divided by 2. Let's put that into perspective. For a tiny system of just 5 variables, Gauss takes about 42 operations. Gauss-Jordan, that takes roughly 62. That is almost a 50% jump in the required computational load. Because of that massive jump in required operations, Gauss-Jordan is actually incredibly inefficient for large economic models. I mean, when economists are dealing with tens of thousands of variables, computational power really matters. So standard Gauss elimination remains the undisputed, most efficient algorithm for running these massive economic simulations. Section 5. Optimizing the economy. Okay, so linear algebra organizes all that chaotic data. But calculus? Calculus is how economists actually optimize for profit. It allows businesses to analyze these tiny incremental rates of change. They look at marginal cost, which is simply the cost to produce just one more unit of a product. Then they look at marginal revenue, the money they make from selling that one extra unit. By taking the mathematical derivative of the cost and revenue functions, businesses can pinpoint the exact moment of maximum profit. It happens exactly when marginal revenue equals marginal cost. If you produce any more, you lose money. Produce any less, and you're leaving money on the table. We also see calculus applied with the elasticity of demand. This is a crucial concept. It uses limits and derivatives to predict exactly how consumers are going to react to a price hike. If the math shows that demand is inelastic, a company knows for sure they can raise prices without losing sales. But if it's elastic, they know a price increase will absolutely crater their revenue. It's basically mathematical fortune telling. So, the crucial point is this. The underlying math of our economy, from those giant augmented matrices to the precise derivatives of profit maximization, is absolutely flawless. It's beautiful. However, the models built on top of this math rely heavily on one very specific, very fragile assumption. They assume that the human beings making these financial decisions will always act as perfectly rational actors. Which leaves us with this final, incredibly vital question. The math works perfectly on paper, but if the global economy relies on perfectly rational subjects, what happens when human unpredictability, panic, or irrational exuberance breaks the model? It's the ultimate tension, really, between the cold, precise beauty of mathematical equations and the wonderfully chaotic reality of human nature. Thanks for joining me for this explainer, and keep questioning the numbers around you.